Rob Rallo, and welcome to our webinar for this month, Basic Standalone PV System Sizing. There's a lot of material we're going to try to cover rather quickly. So, and we may end up going a little over just to give you a warning on this. If you miss something or if you have to drop off for any reasons, as always, this webinar will be available online shortly after this presentation, and you're welcome to go back and review any of the information and materials again or finish whatever parts you may have missed. Again, I've been in the solar business for over 25 years. SunWize has been in the industry for over 20 years. And we focus on, SunWize focuses on distribution and off-grid systems. Again, we're really concentrating on the off-grid and not grid tie systems on this. We have sales offices and warehouses throughout the country. And again, some of the stuff we do is hybrid systems, battery backup systems. We can also provide other services, troubleshooting, installation services, training. Okay, so let's get into, again, because there's a lot of information here. We're going to go ahead and dive right into it and try to get through it in an hour as best we can. So again, this is basic system sizing. So we're looking at is kind of the back of the envelope estimate ballpark. This will get you in the range. It may not be 100% accurate, but it'll hopefully get you about 90% of the way there. Okay. Right now, if we have time at the end, we're going to try to get into some of the slightly more advanced things you need to be aware of, like battery derates, for temperature aging, etc. How would you do a sizing with a maximum power point tracker? How do you handle 60 cell modules? And perhaps a little bit about loss load probability calculations. So what we're going to try to cover here is initial considerations for your system, the sizing methodology, performance and losses, load calculations, which are very important. We'll get into that. Array sizing, battery sizings. We're going to do a few examples, and again, there's other topics I mentioned before if we have time. Okay, again, this is a standalone, which means the solar array is the only charging source. We do not take into account wind, generators, or anything else. This is strictly where the solar array is the only charging source for the system. So all energy to the load is going to come from the sun. And because of that, you need to limit or eliminate any possible shading. We're going to talk about that a little bit more at the end, but shading, if there is, can be a very serious problem, again, because this is your only source of energy from the sun. If there's a shading, we have some serious problems. And again, we'll try to talk about that briefly at the end if we have time. If not, please see your tech note on that. Okay, so along with that, a couple other considerations to keep in mind is that for off-grid systems in North America, you're trying to maximize the energy to the load in the month with the least amount of sunlight, and generally it's going to be the winter. So generally you're always going to target that winter month, December, January, because that's the month with the shortest amount of sunlight in it for North America. Okay, and again, and typically you're going to go tilt angle of anywhere between 45 degrees and 65 degrees south facing for North America. If you're working in South America or other countries, that might be slightly different, but for here in North America, you're going to most likely tilt your array between 45 and 65 degrees from horizontal, and you're going to have it faced true south. Okay, and again, because of that, sighting is very important. You want to minimize or eliminate any shading as much as possible. You want to look for objects like trees, poles, fencing. A big problem is a lot of times this might be for communication sites. You might have towers or things like that. You want to try to eliminate those or move those such that they're not shading the array at all. Especially fences. Fences can be a problem because people are worried about security. If that's the situation, raise the array up so you're above those obstructions like fences and things like that, enclosures or buildings perhaps. Okay. So with that in mind, there are 5 basic steps to sizing. You need to identify the sun hours available at that location. We're going to use a sun hour map for that, but there's also other resources as well. I'll talk about that briefly. You're going to calculate or make some assumptions on system losses, and then you're going to calculate the total load. That has to be in amp hours per day. That's very important. Batteries are going to be storing in amp hours per day. Everything's going to be done in amp hours per day, not watts or watt hours, as some people might be familiar with from grid-tie systems. Again, this is off-grid. We're working strictly off the batteries. There's a storage mechanism, and all the energy is coming from the sun, so you must work in amp hours per day. And then based upon all of that, we can get in, then we can size the array and then size the battery bank. Okay. So just some quick definitions with that. One of the things we're going to mention quite a bit is array to load ratio, or ALR. Okay, and that's a very, very important number, and that is basically the ratio of the amp hours produced by the solar array divided by the amp hours consumed by the load. Okay, and that's very important because you always want to make certain you have more energy produced by the solar array than is being consumed by the load. Otherwise, the system will not work, and you're going to need to have a little extra to recharge your batteries, as well as some other things we'll talk about as we go through this. Okay, autonomy, that is the amount of time that the battery can support the load without any charging source. You'll typically hear that referred to as in days. If you're familiar with UPS systems, they usually do it in hours, but in solar systems, we have to work in days in order for the system to work right, and we'll get into that, of course, in more detail. And then sulfation. I bring that up because it's very important. If your system is undersized or not sized correctly, you're going to find that the batteries will sulfate, which is crystals that will grow on the plates and will then shorten the life of the battery and the capacity of the battery. Okay, sun hours, also very important to understand what that is, because that's the methodology we're going to use for sizing the system. Okay, and basically sun hours kind of equates to kilowatt hours, is the amount of kilowatt hours you're getting out of the system on a daily basis. Okay, and again, we're going to have some maps and stuff on that. Keep in mind that we're working again in the worst month situation. And just some general guidelines, and again, we'll go to the map for that in a second, but some general guidelines are areas with low solar resources are going to have 1 to 2 sun hours a day, medium about 2 to 4, and then places in the deserts might get as much as 4 to 6 sun hours a day. And here's kind of just a general idea of the map. Again, if you look at the color coding, you'll see that some areas can be higher than 6 sun hours a day. You're talking very center of the deserts, which aren't going to really be applicable in the U.S. In the U.S., you might find 5 hours maybe in parts of Texas, definitely throughout Arizona and parts of New Mexico. You might see numbers that higher, even Southern California. Generally, though, for most of the U.S., you're going to be somewhere between 2 and 4. In areas around Seattle or Boston, you might find it might be a little less, maybe about 1 to 2. They get some really lousy sunlight in those areas. So again, if you're going to look at the yellow, you're going to be looking at somewhere around 2 to 3 sun hours a day. I would recommend always being conservative and using the low end of that. So unless you're really on that line between 2 zones, I would generally try to use the lower number, not the higher number, just to be conservative. As always when doing this, it's better to be conservative and have your system over-designed than have it under-designed and have it fail prematurely, or to have the batteries fail prematurely from sulfation, from not getting charged properly. Okay, the size of methodology we're going to be using is the sun hour method, as I mentioned earlier. All of this is based upon IEEE standard 1562. That is the guide for array and battery sizing and standalone PV systems. I highly recommend, if you want to learn more about this or go into detail, it has a worksheet as well that you can use for going through the calculations and everything. Highly recommend you go out and purchase that standard from IEEE. It's a very good standard. There's a lot of good information in it. It'll go through stuff in a little more detail. Again, it has that worksheet in it and has additional examples you can go through as well. So I highly recommend that if you want more information on how to do this. And again, as I mentioned before, sizing is always based upon the worst case solar installation, but also we have to keep in mind the highest load consumption. There could be a situation where you have an air conditioner, perhaps, or something like that, which is going to cause the load to actually be higher in the summertime than in the wintertime. So you do have to check that for various months if you have a variable load. Generally, most of the loads you're going to find are either going to be consistent on a monthly basis, or if it isn't, it's going to be kind of a lighting load, which is generally going to be worse in the winter anyway. Rarely do we find one that's worse in the summer, but if that does happen, you will need to go through several months of calculations to double check that. Again, that's a rare situation, but just to make you aware of it in case you do come across that. And always, of course, take into account the greatest losses and the highest load consumption. Again, we're looking at, we're always trying to be conservative, rather have its system slightly oversized than to have it undersized and not work or fail prematurely. Excuse me. Okay. Again, the solar array is there to replace the amp hours in the battery that's being consumed by the load. So again, you're really sizing the array to that, and because they're always working in amp hours, and because of that, you want to oversize the solar array slightly, not just for the system losses and efficiencies, but also to be able to recharge that battery. A lot of people think a bigger battery is better. It isn't always better, because if you go with a massive battery, say maybe a 30-day battery, and you drain the battery down, and you've sized your array very small, maybe just maybe just 10% over, then it's going to take a very long time for that battery to get back to a full charge. And if you're familiar with our other webinars we've done, we talk about how if the batteries don't get fully charged periodically, they can sulfate. And again, that's the problem. If you go to too big a battery, that can be a situation. So bigger isn't always better. So it's best to have a battery sized appropriately to your site and your situation. And if you do have to go to a big battery like that, make certain you oversize the array such that you can recharge that battery quickly, or at least fast enough that you're not going to have a sulfation issue. So if you do oversize the battery, you have to oversize the array to compensate for that. Also, along with that, if you're looking at long-term installations, systems that are going to be out there 5, 10, 20 years, also keep in mind, and you may want to factor some of these into the system losses. I'll talk about that more when I get to it, but I know sometimes there are people that will design in the fact that solar modules do degrade over time, up to about 1% per year. So some people may put in additional losses of 20% because they want to have a 20-year design life to take into account the solar array, or they may add additional 20% because of the battery degrading over time. So people may actually build in into their D-rates and losses these types of things over time. So something to consider when we get into those losses, but just keep that in mind now. And along with that, perhaps just some of the warranties on some of the equipment too. Okay, there are two important numbers that will make or break how your system works. Okay, one is the accuracy of your load data, and the other is accuracy of the solar installation data that you have. Solar installation data, believe it or not, actually is very accurate. We have lots of good numbers and resources for those. Way more accurate than the map I showed you before, and at the end I will mention some of those resources and where you can go get those. But the load is always dependent upon the customer, whoever's equipment it is that's going to be installed. So that's not one, and they may not always understand what their load is, and that can be a bigger problem. But again, the performance of the system is only as accurate as that data. Again, if you have decent site location, you can get generally pretty accurate solar installation data. It's the load that can be a problem. If the customer does not fully understand their load, then you may have problems with the system, so keep that in mind. Again, as I mentioned before, if you undersize your system, it's going to fail prematurely. You're going to have batteries are going to fail prematurely. You're going to have a lot of expenses with troubleshooting trips and having to replace batteries frequently. On the other hand, if you oversize the system too much, then you may have spent money that didn't need to be spent. Again, you want to oversize a little bit, but not too much. You don't necessarily want to double the size of the system because you've doubled the amount of money you have to spend on it. The cost of systems are generally linear. When you get to very tiny systems, that may not be true, but for the most part, it is linear. So however big the load is, it's however big the system has to be. So if you've doubled a lot of the stuff, then you've doubled the cost of the system. So again, you want to try to be as accurate as you can while still being conservative in the numbers, and that should get you a good performing system at a reasonable cost. And some of that may actually have to do with the critical nature load, and I'll talk about that again too. IEEE does talk about that, about using different numbers depending upon how important the load is. Okay, so now we're going to talk a little bit about the system losses. System losses are generally something you're going to have to try to estimate or assume. And these are things that may be dust on dust accumulation. We may want to take that into account in the modules. Battery inefficiencies like the Coulomb effect of the batteries. Again, there are losses there when you recharge your batteries. They're not 100% efficient. There are losses there. Batteries usually give that off in the form of heat. There could be other parasitic losses, like the charge controller itself consumes a little bit of energy. You may want to take that into account, these numbers. You may also want to take into account some other types of losses like that. Like I mentioned before, maybe derates for aging or something like that. And if you look again, if you go back to IEEE standard I mentioned before, they'll mention some other ones in there as well. They have a little worksheet on that. And again, there may be other losses you might think of as well. These are just some of the typical ones I've mentioned here. Again, we usually these losses are somewhere between about 10 to 20%, and those are based upon 10 to 20% of the actual system or the load. Okay, so now we're getting the load calculations just a little bit. And again, I mentioned everything has to be in amp hours per day because that's how all the sizing works. That's how this set-hour methodology is used. That's how IEEE recommends we do it. So whatever form of information you get the load in, you have to convert it into that. If you get it in amps, then you multiply by 24 hours to get amp hours per day. If you have it in watts, then you have to divide by the voltage, and then multiply that by 24 hours to get amp hours per day. And if you have it in some other form, you have to do calculations. I would also like to mention that that is based on system voltage. If you have things that are not at system voltage, you have to take that into account as well. And I'll show a couple examples of that. You may have to put in the inefficiencies of a conversion process from a DC-DC converter or an inverter or some other type of power conditioning or conversion equipment. And then you would go with the watts, and then you would divide by the system voltage to convert that back into the amp hours per day at the system voltage. And again, I want to clarify that that is the amp hours per day at the system, not the load, but at whatever the system is, because again, we're calculating this for the battery and for the solar array to recharge the battery. Okay, and if you have a non-continuous load, sometimes you might have I'll show some examples of that again too, but you might have like a radio that's transmitting. It may transmit 1 hour a day. You may have a pump that only comes on for 5 or 10 minutes a day. Then just go ahead and use that number. So it would be, so I don't know, you may have a radio that operates so maybe 10 amps for 1 hour a day. Then you go ahead and multiply that 10 amps by the 1 hour, and that'll give you your amp hours per day for that, which of course would only be 1. Which is 10 amps. 10 times 1 would be 10 amps, 10 amp hours a day. Okay, so in this example, we're a couple examples here. We have a 3/4 of an amp load, so 0.75 amp. It's continuous. It's 24 hours a day, and it's going to be 24 volts. So we're going to go ahead and multiply that 0.75 by the 24 hours. We're going to get 18 amp hours a day. And again, that is a 24 volts. So that's the system voltage we would use would be 24 volts. Okay, the second one is we're going to have a load that's in watts. We're going to have 15 watts continuous at 12 volts. So we're going to have to convert that to amps. So if you divide the 15 watts by the 12 volts, you're going to get 1.25 amps. Then you're going to go ahead and multiply that by the 24 hours. It's going to give you 30 amp hours a day at the 12 volts. Okay, so it's very important. And you could have multiple loads too. And I will show examples of multiple loads later on, but you have to add those up. So let me go back just a second. So again, if you had, you could have multiple loads at different voltages, and you're going to have to kind of get it all to amp hours per day at the system voltage. Okay, and we'll do an example at the end that shows one with 2 or 3 loads where you will have to go ahead and average them out for the system voltage. As I mentioned before, if you have loads that are not the system voltage, whether it be DC or AC, you're going to have to include those inefficiencies in your load calculations. Generally, those can range anywhere from, say, 80% for DC-DC converter to 90% for an inverter. Intermittent load should be averaged out. As I mentioned before, if you've got something that's on a daily basis, then you just go ahead and figure out your amp hours per day based upon that. If you have something that might be on a weekly basis, then you can try to average that over the 5 or 7 days of your battery autonomy. Or you can just be conservative and assume it's going to be every day. Future expansion, that's something else to keep in mind in your considerations and your calculations here. Frequently, if you have a telecom site, there might be expansion. If you're at some other place, you may be adding on additional equipment or maybe additional SCADA or monitoring type of stuff. So you may want to include that in your considerations early on. Just put a little extra safety margin in there for that. If you have loads that might be polling, you may want to add additional safety margin there for polling. It may be more often than you think it is or something like that, especially when you're dealing with radios and pumps. So take those, please, keep those considerations in mind and take those into account and be conservative with your calculations on those. Generally for inrush on AC loads, you need to size your inverters and equipment for that. But it doesn't usually come into account because it's so brief. It's only for usually a few seconds. It doesn't come into account for your sizing. It's only important to make certain that your power equipment can handle it, but the system sizing doesn't really care, again, because it's only going to be for a few seconds for inrush currents. Okay, as I've mentioned several times, we're going to be referring back to the IEEE 1562 for this. And again, your design is only going to be as accurate as the solar data and the load data that you're using. And of course, be conservative with your system losses. And I mentioned before the difference between some non-critical and some critical loads. IEEE actually breaks that out, and they say if you have non-critical loads, maybe lighting or something like that, and you're in an area with some high solar insolation, then you can use an array to load ratio of about 1.1 to about 1.2. In other words, you're saying don't oversize it that much. If the load goes down occasionally, it's not that big a deal. But if you're in an area with low solar insolation or with a critical load, maybe some type of oil and gas monitoring, or maybe a telecom site that's very important, especially if you're working with municipalities where you don't want your fire station radios and stuff like that to go down. You're going to want to go to a higher array to load ratio of 1.3 to 1.4. Again, so I mean, so how conservative you are with your design may depend upon how critical your load is. If you're going with a very critical load, something that's very important, you don't ever want to fail, then you may want to go ahead and oversize your system a little bit more to make it more reliable. If it's something you're not really as concerned about, say again lighting or something like that, then you may want to go to a slightly smaller design. And if it fails, once every 5 years or so, not that big a deal. So the rate calculations work like this. You take your load in amp hours per day, okay, and you're going to multiply that by the system losses plus 1. Then you're going to multiply that by the rate of load ratio. Okay, and basically that's going to oversize the array. Then you're going to divide that by the number of sun hours you're going to get in the day, multiplied by the maximum power point current of the solar module. And that's going to give you the number of modules in parallel. So the number of strings you're going to need. The number of modules in series, I'm just going to briefly talk about that. We don't have any slides on it. But basically the number you need in series is just going to depend upon the modules you're using and the voltage you're working. If you've got a 12-volt module, it's a 12-volt system, then obviously only 1. If you've got a 12-volt module and a 24-volt system, you would need 2 in series. If you're working with a 24-volt system and a 24-volt module, then you would only need 1 in series. Again, just so long as, and again, this is for 36 or 72 cell modules. This methodology is only for that. If I have time at the end, I'll briefly talk about to do with 60 cell modules. But at this point, the number of modules in series would just be whatever you need to get your system voltage. So the sizing calculations are only for the number you would need in parallel, the number of strings you would need of those modules. So let's just briefly go through that example here. Let me again, just to highlight a few more things here. Again, the maximum power point current, that IMP, that is your selection. You may want to go through a couple of iterations. If you're finding you have a whole lot of modules in parallel, you may want to go to a bigger module. If you're finding that you've gone to too big a module, you want to try a smaller one, perhaps, if you've got a smaller load. And of course, as I mentioned before, that rate of load ratio is dependent upon the critical nature of your load. And you may need to go through a couple of iterations, as I mentioned before, depending upon the module you're using. If you've got a large load, you may just want to go ahead and go to a big module. If you've got a smaller one, you may just want to start with a smaller module. But you may want to go through a few times until you come up with numbers that make sense. And so let's just run through these calculations really fast. As using that example we had earlier of the load that ended up being 18 amp hours a day, we're going to take that 18 amp hour day load, we're going to multiply that by the system losses of about 20%, which is usually a pretty good average to use. So, and then we're going to multiply that by a regular ratio of 1.3. Okay, then we're going to divide that by the sun hours of 2.5. Excuse me. And we're going to use a 110 watt module, which has a IMP of about 6 amps. So if you do all those calculations, you come up with about 1.9 strings. Now, you can't get a 0.9 of a module, so you always need to round up. And I want to make that, I want to kind of highlight that it's very important, even if it's only 1.2 or 1.2 modules that it comes up with, you always need to round up. Because if you round down, you've made your system too small. If you're finding that that number ends up being small, like if you're at a 0.2 or a 0.3, you may want to go to a slightly smaller module to make it bring it back down so that you're more around the 1.8 or 1.9 or whatever. Or if you're on the other if you've gone bigger, it could be 3.8 or something like that, or even a 0.8. But again, if it's one of these things, remember you always have to round up. You can never round down. Very important, because if you round down, you're going to have your system be too small, it's going to fail. So if you find that if you're on the limit of the number, you may want to adjust your module and try a module with a different current rating to have it be a little bit more cost effective, so this design is a little bit more efficient. So again, so we rounded up, so we need 2 strings in parallel here of the 110 watt modules. So moving on to how do you do the battery calculations. Similar to the solar array, IEEE 1562 also separates out the critical from the non-critical loads with regards to autonomy. If you've got a non-critical load or areas with lots of good sunlight, then a battery autonomy of 5 to 7 days is fine. But if you've got a critical load or area with some bad sunlight, they're going to want to go to a 7 to 14 day battery. Again, areas like Seattle, Boston, really, they could go weeks without sunlight. So that 14 days, although it may sound large to people in the desert, if you're in the Boston or Seattle area, that 14 days is what you really need, and even then you can still have problems. So it's not unusual to be using a 14-day battery in those locations. Then if you're in the deserts, and if you're in Texas or Mexico, Arizona, or Southern California, we've got really good sunlight, 5 days is pretty good. And I want to highlight the fact that notice they don't recommend anything less than 5 days. If you have people that are trying to do a 2-day or a 3-day battery, they're not following the standard. Again, the industry standard is IEEE 1562. It's the only one out there, and they do recommend nothing less than 5 days. And that's for a good reason. Again, it's for proper performance of the system, it's for proper performance of the battery, and it's for a well-designed system. If you're going for less than that, you're going to have premature battery failures, you're going to have premature system failures, and again, you're working with people that aren't following the standards. So it's very important to be going with a battery that has a minimum of 5 days. Also, take into account, this doesn't. Also, want to mention, it's not taking into account any type of derates yet. And again, if you have some time at the end, I may get into those. So just to highlight some of the derates, temperature is a big one that could come into effect, and just being right around freezing, 32 degrees Fahrenheit, 0 degrees Celsius. Your battery capacity is already reduced by about 15%, so it can get about 85% of the battery at that temperature. And it's not unusual, in most places in the U.S. to be, around freezing in the wintertime. So just one of the things to think about. You may have to oversize the battery to take into account. And again, if I have more time at the end, we'll talk about that in more detail. So to go through the calculations on that, again, we take the load, then we multiply that by the number of days of autonomy. And then we're going to divide that by the maximum depth of discharge, and that gives you your battery capacity. For most deep cycle batteries, you can go to about 80% depth of discharge, And I want to bring up the fact that you can almost never use 100% of a battery. If you discharge your battery 100%, you're going to two things are going to happen basically. One is you're going to shorten the battery life dramatically. As a matter of fact, it may not even come back. It's like leaving the headlights on in your car. Overnight, the battery will most likely be dead and not come back. You're kind of doing the same thing with discharging a battery completely here. The other thing is that when you do that, there's a voltage collapse that occurs too. So at some point, your load's going to shut down. Because if it's a 12-volt battery and you continue to discharge it, it's going to discharge down to 6 volts or 4 volts or something like that until you've pretty much damaged your battery. But your load cannot operate at 6 volts or 4 volts. So again, there's going to be so there's only a certain usable amount of the battery you can use. Generally, and again, in a good quality solar deep cycle battery, you're looking at about 80%. So most of the time, we're going to use 80% depth of discharge. If you want to get a little bit longer battery life, or if you're using a battery that isn't very good and not designed for solar, some shallow cycle batteries that people use frequently in third world countries like in Africa or South America or Southeast Asia. If you're using a car battery, basically, those aren't designed for deep cycling. You can only use about 50%. So we'd use 50% in that situation. But again, for most of the time, you're going to find that the 80% DOD is probably pretty good. So just to go through it again, you take the load times the battery days of timing that you want divided by the discharge rate. Okay. So if we go through an example of that, using that same 18 amp hour a day load we mentioned before, we're going to go with a 7-day battery. So we take that 18, multiply by 7, and divide by the 80% DOD, and you're going to find you have a battery, a required battery capacity of 157.5 amp hours. Now, what that may mean is you may not have a battery that's exactly 157 amp hours, and generally you're going to find out you don't. So just like with the solar array, you're going to want to probably go up the next size battery. So most group 27 batteries are about 100 amp hours. So you may want to use 2 of those. So you may end up using a 200 amp hour battery instead. But that's what happens. You just have to go the next size up. You could use a group 40 battery, which is rated around 200, 210 amp hours, or whatever combination of batteries you need to use to get to that. Again, that's the minimum that you need. It's always okay to go a little bit bigger. And like I said, just to the solar array, you may have to play around with the batteries to find the one that may get you that capacity that is the most efficient, most cost-effective one for that load or for that application. And again, just going through the map and again showing you some of the worst month average. As I mentioned, there are other sources for that besides that map. One of the better resources that's been around for decades, and I mean it literally has been around for decades, it's been around since the late 80s, is something called the NREL, National Renewable Energy Labs Red Book. They came out with that in the late 80s, updated again in the early 90s. And it's got, hundreds of sites across the United States, which includes Hawaii and Alaska. And you can go to the website link that I have there on the screen, and basically it gives you the numbers in sun hours. Again, as I said earlier, if you go back to definitions, the sun hours do equate to kilowatt hours per meter squared per day. So it'll give you those numbers. And because we're always working and we're in the worst case month, you're going to have to go down and find it. And I'm not exactly certain what this example is, what city or location, but you can see here in this case the worst month is December, which is typically, again, for most of the U.S. is going to be December, January, and it's going to give you 3.8 sun hours a day. So you get a little more accurate than that map. We're using resources like this. Do notice that generally, if you're going to use a resource like this, they may give you multiple data for multiple different angles. This one gives you an angle of 0 degrees to 90 degrees, which is basically horizontal to vertical. They give you a few other ones in between. For the most part, the optimum angle, tilt angle, is going to be latitude or latitude plus 15 for most locations in the U.S., which ends up equating the summer between 45 degrees and 65 degrees. So generally, if you're going to use the NREL N book, I would recommend using that latitude plus 15. And again, that'll give you a little bit more accurate than using that map. The problem is, again, there's several hundred data points, but you may find that there's one that isn't, so you may have to go to the map or some other method of that, like trying to approximate what it might be. I generally just try to use the nearest major city that I can find data for out of the Red Book. So let's go ahead now and go through a couple of examples. This one's going to be really simple. We're going to go with a load is going to be 15 watts at 12 volts. It's going to be continuous 24 hours a day. Location is going to be Huntsville, Alabama, and system voltage is going to be 12 volts because that's what our load is. And if we use NREL or some other source, we can find that the exact worst case set hours a day for that location is going to be 3.23. But because we're going to use the map, we're going to go ahead and be conservative and use just 3 from the map, just for sake of discussion here. Okay, we're going to go ahead and just go with 10% on the losses. It's a pretty simple system, so we don't really have a lot of losses to worry about. So we'll just go ahead and use 10% for that. So then our next step is to go ahead and calculate the load in amp hours per day, and then we're going to size the array and do the battery. So again, just a simple calculation. We're going to take the watts, divide that by the voltage. It's going to give us the amps. They're going to multiply that by the hours per day it's operating, which is because it's continuous, that's 24 hours a day. That's going to give us 30 amp hours per day at 12 volts. So going through those calculations now, take 30 amp hours per day, we're going to multiply that by basically 1.1 for the losses, and then 1.2 for the AOR. And again, we're using the 1.2 because it's not that critical of a load. Whatever it is, we could assume it's lighting maybe, or I know it could be maybe meteorological stuff. It's just not that critical. So you're just doing some monitoring of the weather or something like that. So 1.2 is fine. We're going to divide by that 3 sun hours a day, and also by 7.8 amps. And that is the in this case we decided to use 140 watt module. So that would be the current at peak power for 140 watt module is 7.8. And if you multiply that out, you're going to come up with 1.7. And again, you have to round up to the next one, so you have to use 2 strings. So it's going to be 2 140 watt modules in parallel are going to be needed to support that load. Okay, so then we can go through the battery, and we'll take that same 30 amp hours per day, multiply by 5 days, and we're going to go to because it's not that critical. And then again, we're using a deep cycle battery, so we're going to go ahead and use 80% depth of discharge, and that's going to give us 187.5. As I mentioned before, you're going to have to go to whatever the next size up battery would be. In this case, you could go with a single 4D, or you could go with maybe 2 of the group 27s in parallel. We do try to recommend going with no more than 4 strings of batteries in parallel. Or less. And if you want more information on that, I think we have tech notes on our website for that. If you get too many batteries in parallel, you start having various issues, so you want to try to minimize that. You can go with 1 or 2 strings, that's usually the best. If you have to go up to 4 strings, that's okay too. But again, you want to try to keep those at the minimum, and if you want more information on that, go to the tech notes section of the SunWize website. Okay, just to try to summarize the results of that, we used 3 sun hours a day. We used 10% for system losses. Our load calculated to be 30 amp hours per day. We ended up using 240 watt modules. That's a 280 watt solar array, and we found the minimum battery size that we needed was 187 amp hours. Okay, so let's do another example now. We're going to make this a little more complicated. So now we have a couple of things. We've got a load that's not continuous. We actually have a couple loads that are not continuous. And we've got one that's not at the system voltage. We're going to go ahead and use a system voltage of 12 volts, but now we have a 24 volt load. So let's assume this a good example of this might be some radio equipment. A lot of times the radios only transmit for 1 hour a day, and they're sitting there on standby. They're the 23s. So this is pretty common to have a load like that. So let's say the location is going to be Boulder, Colorado, and again, if you go to if you wanted accurate data, it's going to be 4.5 sun hours a day, but we're going to go ahead and just use 4 from the map just for discussion purposes. Okay, and we're going to assume that we're going to assume a 20% system losses on this one. Okay, so let's go through the load calculations again. They get a bit more complicated. So that first load was 15 watts at 24 volts. So we're going to have to divide that by the losses of the conversion equipment. So we're going to have to use a 24 volt to 12 volt converter. So there's usually somewhere between 80 and 90% efficient. So we're going to go conservative and use 80%. So we can divide that 15 watts by 80% first. And then we're going to divide that by the 12 volts system voltage. And because it's only operating 4 hours a day, we're going to multiply that by 4 hours. That's going to give you 6.3 amp hours per day. So that was load 1. So the second load now is 5 watts at 12 volts. We're going to divide the 5 watts by the 12 volts, multiply that by 23 hours. We're going to get 9.6 amp hours a day at 12 volts. And then the last one is a little bit simpler. It's just 1 amp times 1 hour, so it's just 1 amp hour a day at 12 volts. So now if you add all three of those up, you're going to get total load of 16.9 amp hours per day, and that's what you can use for sizing. Okay, so now if we go through the formulas again, we're going to have 16.9 amp hours a day. I'm going to multiply that basically by 1.1 for our losses, another 1.2 for our losses, another 1.2 for the non-critical, the ALR for the non-critical load. Divide that by the 4 sun hours a day and the 6 amps. We're going to go ahead and go back to that 110 watt module again. We're going to come up with a 1.01. Now, because if you round, this is one of these where if you rounded it off, it'd be about 1.1. You can get away with one string. If you're right around that, that 1.1 or less, if you've got a 0.1 or less on that one, you may want to think about just rounding down. Depends on the critical nature of your load. You may just want to go to a slightly smaller module maybe instead, or a slightly bigger module, whatever you want to do to try to, in other words, if I was a little concerned, I could have maybe bumped up to 120 or 140 watt module, something like that, to get that current up a little bit, and maybe get to like a 0.9 string. So something is to think about. Again, you may want to go through a couple of variations with a couple of different modules to figure out which one works best for your application. This one's almost dead on at the 1.01, so we're just going to go ahead and go with that. So we only need 110 watt module for this example. Battery calculations, again, fairly straightforward. The 16.9 amp hours a day times 5 days, again, because it's not critical. Divide that by the 80% depth of discharge, and you're going to get 105.6 amp hours. And generally, that's going to probably just be one Group 30 battery. Group 30 batteries are usually somewhere around 108 to 110 amp hours. So that would be appropriate for that. So just to summarize that example, we used 4 sun hours a day, 20% for system losses. Calculated the load to be 16.9 amp hours a day. Ended up just using 110 watt module, so it's just a 110 watt array, and the minimum battery size needs to be 105.6 amp hours. Okay, I just want to again reiterate some of the most important things about sizing. Again, you want to make certain that you're conservative in your design. Again, better to be slightly oversized than to be undersized. You want to make certain that you have as accurate a load data as possible. You want to try to go with as accurate of solar insolation data you have as possible. If you're not certain, again, go to the lower one. Always better to go to the worst case scenario. On the ALR, again, 1.3 to 1.4 for critical loads. 1.1 to 1.1 and 1.2 are okay for non-critical. The battery, 7 to 14 days. Again, the 14 days if you're up in some really bad areas of the U.S. and the upper northeast and northwestern corners. You're going to find that the sunlight there is pretty bad. And I just cannot highlight enough the fact that a 5-day battery should be the minimum you're using for this. Okay. How are we doing? Okay. Errol, do we have any questions we should address first, or do we have about 10 extra minutes? Should we get into some of the additional considerations for sizing?
Well, actually, I just got a question on some larger loads. So, given the time before we hop into this, maybe we can actually just kind of pencil out a larger load and do kind of the exact same thing, but maybe see where things land.
Okay.
I was thinking maybe like 100 watts continuous. It's a pretty large one.
Okay. So let me just
You could almost just like create some new slides and make it, or just edit the existing slides. We can just override it on this version and go through the loads really quick.
okay. Um, so let's go back to load
Yeah, it's
one.
a simple one.
Here we go. Just keep it simple. There we go. Let's get oops. Okay.
Let's just do 100 watts and we'll go through it really
Okay.
quick.
So yeah, so we'll just go ahead and make this 100 watts, and we'll go ahead and use Huntsville, Alabama again. Um, okay, so let's go through the load calculations. So it would just be 100 watts at 24 volts. It'd be 100 watts divided by 12 volts.
So that's 200 amp hours per day. I'm not sure if
Yep,
you have a
exactly.
calculator too, Rob.
Correct. That's what I just got to. Okay, well, it's 200. Go to the next slide. So if we plug 200 in here, okay, so we're going to multiply that times 200 times 1.1 times 1.2. Divide that by 3 sun hours a day. Divide by 7.8. I come up, oops, I messed that up. Okay, divided by 3, so that's 88 divided by 7.8. So I come up with 11.28 strings. And then again, this is one of those where you need to round up. So I would need 12 of these 140 watt modules in parallel is what I come up with. Okay, so about 11.28 or 11.3 is the number of strings I have for that. Okay, let's put a few modules. But
Thanks,
then
Rob.
again,
I,
okay.
all right,
Okay,
I've got
now,
one more quick question before we maybe jump on. I don't know if we want to do the battery section also, but I think folks get the idea.
yeah, I think
Basically,
it's
get the
pretty.
exact same thing, and then you're going to be limited, by finding a big enough battery that you can get in 4 or less strings, or go into an industrial battery or something like
Yep.
that. I do have a next question on factoring in snow covering in places where we do get snow cover in the winter, and how that might be able to be estimated or factored in.
Very good question, actually. Generally, two things with that. Number one, usually that would work in your battery autonomy. So you're going to find in those locations in the country where you have a lot of snow, you're also going to have some bad weather. So generally, you're going to want to go to that 14-day battery for that. And what will end up happening is because your solar array is also going to be at least a tilt of 45 degrees, generally higher, again, for those areas of the country where you get snow, you're going to probably be going to a 55 or even 65-degree tilt. The snow will slide off. It's just glass. So although it may be on there for a brief amount of time, generally it will just melt and slide off in a few days. And that day or two that you may have lost will usually be taken care of because, again, you're going to be in an area with lower sunlight insolation. So you're going to want to go to that higher battery autonomy and the higher array to load ratio. You're going to want to go to that 1.3 to 1.4. So you wouldn't necessarily take that into account in terms of the system losses itself, but you would take that into account by looking at it as an area with lower sunlight. So you're going to want to go to, again, a higher rate of load ratio and a number of days of autonomy for the batteries, how you would take that, how you would factor that in.
Thanks, Rob. I do have one more question about understanding battery sort of manufacturing and design differences between traditional automotive batteries that might still be sort of ERLAs and deep cycle solar batteries. What exactly about it is, what exactly about solar batteries makes their deep cycle performance so much better than other similar batteries?
There are a couple of differences. The main one is the plates themselves. In a car battery, you're going to have thinner plates, but more of them. So you have more surface area, so you get a lot of current off of them for starting a battery. It's where you get that cold cranking amps from, so they create a lot of surface area to get lots of current. The problem is that when you do that, because the plates are thinner, they don't want to cycle very deeply because the plates are very delicate for that from that perspective. So in a deep cycle battery, you're going to find there are less plates, but they're thicker, so that the plates are more robust so they can take more abuse in the deep cycling. There can also be some differences with regards to the electrolyte being used, basically the acid, and also with regards to the alloys in the plates. You may have calcium or antimony or something like that in there. Frequently, antimony is put in also to make the plate stronger so they can handle the discharging. I think we might have some stuff on our some tech notes on that as well. Or there's also a couple of IEEE. Again, there's some IEEE standards on that also, with regards to though. I think it might be 1361 or 1362. It talks about battery types used for solar applications.
All right, Rob, I got a question that I think came up a while ago from somebody, but is there any technology or components that are available to help minimize partial shading? I think we talked about this with maybe one of the charge controller manufacturers about kind of some technologies that were apparently out there, but do you want to rehash that again, Rob?
Well, it depends quite a bit actually upon the application, the modules, the voltage, and the maximum power point tracker being used. Excuse me. But certain maximum power point trackers can try to extract um, more energy out of it. But the problem is this: if you're only working with one module and you shaded one cell, there's nothing to extract, basically, because there's no current. So if you have, say, multiple modules and parallel, then it can help to do that. But if all you have is and if they're in series, it's the same problem because again, you've limited that current to zero. So again, it depends on what you're doing. But um, if you go to our tech note, and again, if you looked at that slide I showed earlier, if you shade so much as actually we have uh, no, we're not showing it here, but if you shade so much as one cell in a module, that output goes to zero.
It's
And
back to beginning, Rob, the
oh,
graphic.
yeah, let me just show that real fast. Here we go. Again, if you shade so much as one cell, because all of the cells are wired in series, so that means the current through each cell is exactly the same. So basically, the output current is limited to the weakest cell, the weakest link, basically. So if whatever that current is reduced on that cell, then that's the amount out of the solar module. There's no amount of technology that's going to fix that problem. It's zero, period. There's nothing you can do about it. Now, if you have ones in parallel, there are other things you can do to try to mitigate it. But if you've got stuff wired in series and you shaded that cell, that's it. There's nothing you can do. The exception to that is if you're using a maximum power point tracker and you've wired several in series. Let's say you've got a 12-volt system and you've maybe wired two 12-volt modules in series. Then it can bypass it because there are bypass diodes in the module, so then it can bypass that module out and just remove that module and then go to the second one, basically. But that's if you have multiple ones and use a maximum power point tracker and you've wired them such that the voltage is higher than the battery voltage. So you have to do a few things there. But and this is a problem because so much as a fence post can be a problem, or any other type of pole. I know you might have a pole with a monitoring camera on it that's shading the solar module. And these are things you have to think about because again, if you shade so much as a single cell, the entire current output out of that module goes to zero. And again, all you can do is just bypass that module is the best thing you can do. You can't get anything else out of it. You can just either bypass it parallel wise, or if it's in series, if you have maximum power point tracker and your voltage is high enough, it can just pretty much bypass it with the bypass diodes. So um, yeah, and again, our Technion on it's got some more information on it. Any other questions, Earl?
Rob, I think we're pretty good on questions for right at the moment. So I think we've got enough time. We can go maybe 5, 10 minutes over and cover the rest of this stuff.
Okay, I'll try to go through a few of these additional considerations then quickly. Okay, basically, battery derating for temperature aging, like I mentioned before. Shading, I think we've covered that in pretty good detail at this point, but I will mention a couple of things on that. Max or PowerPoint tracker controllers, 60 cell modules, loss of load, and then a little bit more about the PWM versus MPPT. Some of the battery derates to take into account are temperature and aging, those are the most common ones. Um, and you want to deduct that from the battery capacity itself. So basically, going back to say a Group 27 battery, it's rated. It's about a 100 amp hour battery, but if the battery is derated, so 85% of it's gone at 0 degrees C, then that means that 100 amp hour battery is only 85 amp hours. Okay, and I'll have a curve on that in just a minute. Common age derate is 20%. That actually kind of comes out of the telecom industry because when the battery is reduced to 80% of its capacity, they used to just replace them. So some people would say a battery's failed when it's 80% of what it was. So a lot of times they'll build that into the design. So knowing that the battery will lose capacity over time, so they go ahead and build that 20% into it up front, and when the battery has lost that capacity, then they'll just replace them. But they'll do that up front so that they'll always have that, say, 5-day battery, because otherwise, at the end of the life of the battery, you're now at a 4-day battery, no longer a 5-day. So they'll build that in up front, especially on critical loads. And for temperature derate, uh, I don't know if a battery manufacturer doesn't have a derate curve for that, but refer to the manufacturer of the battery. They should always have a derate curve for that. And again, what's going to happen is that batteries are rated at 75 degrees, basically 77 degrees Fahrenheit, 25 degrees C. Anything above that, the capacity is about the same. They go up slightly. It's below that is where it starts to degrade, especially once you start to get around freezing and colder. They can drop off quite a bit, actually. I think the curve just gets a little steeper at that point. Again, so high temperature affects more of the life of the battery. Doesn't really affect the capacity. The capacity is affected by cold temperatures. And as you can, again, as I was saying, you kind of see it go off more steeply once you break about that freezing point. And then you can see, I mean, basically the time you get to about, in this case, by the time you're about minus 20 Fahrenheit, you're only about 40% of the capacity. So, I mean, half the battery, you have to more than double the size of your battery in a very cold climate just to compensate for a temperature effect. Again, I'll go back to your car battery. It's most in the northern parts of the U.S., most car batteries fail in the wintertime because the capacity has been reduced. When it's colder out. So if you've got a weak battery to begin with, and then you factor in the fact that it may only be 50% there because it's cold out, then that's why it fails so easily. So just something to keep in mind. So having a double the size battery, say, in the Boston area is not uncommon, taking into account their cold winters. Alaska is even worse. I mean, I've seen batteries be triple the size there. Yeah, I think I think we've already got that one a little bit. I think we already talked about that. Okay, shading. I think we've covered that quite a bit. My response to shading is just avoid it. Really, if all possible, just avoid it. It ends up making your system less reliable. It ends up making it more costly. There are There are tools out there that can help you determine if you will have shading issues and when. But trying to quantify what that is always a problem, especially when there could be a hard shadow versus a soft shadow type of thing. A soft shadow might be something far away, where a hard shadow might be, something very up close. Hard shadows are always worse than soft shadows because soft shadows still get ambient light, but a hard shadow won't. But again, it's always just best to avoid it. MPPT charge controllers. Um, I think we had a pretty good webinar on that last time about the MPPT versus PWM. The simplest and most conservative way to size your system is just to size the system, as I mentioned before, and assume you're going to use a pulse width modulated controller. And if you want to use an MPPT, just use an MPPT. And know that you're going to get, again, if you were at our last webinar on that, know you're going to get an extra 5 to 10% increased rate of production out. So you can consider extra design margin. So maybe you might go with, instead of using a 20% for your system losses, you may just go to maybe a 10% instead. Or, instead of using a, 1.3 rate-of-delay ratio, use a 1.2 because you're going to get a little extra out. Or maybe not. Maybe just assume that, hey, you've got a little extra, again, a little extra design or safety margin there. So again, I would size it just the way you'd size it as we did before. Assume you're going to use a PWM, and if you want to swap it to an MPPT, that's fine. Just you got a little extra reproduction that you can use for safety margin or something like that. Um, one of the other places that might come in handy, it would be if you've got a 12-volt system and you're using 240-watt 12-volt modules, as we talked about in that example. That's a total of a 280-watt solar array. You could alternatively use a 24-volt module with the MPPT because let's step the voltage down. Right now, it's pretty. Right now, the 300-watt modules, 24-volt modules, are pretty cost-effective. So you might find that going to a larger module might end up being cheaper than going to so going the 300-watt 24-volt module with an MPPT may actually be a cheaper option for you than two of the 140-watt modules, and you can get because you got more solar from the array plus MPPT, can actually make your system more reliable too. So not only have you made your system more reliable, you save money. So just something to think about and consider. So that's one of the ways using an MPPT could help you. Now you would use the 60 cell modules in the same way. You pretty much just do the same thing. You would have to use the MPPT, but then you could just cross the wattage. The only problem you have to, so again, using an example we had just above there, instead of using, say, maybe you have a 60 cell 280 watt module, you can do the same thing instead. You can go ahead and use the MPPT because it's going to step that voltage down to 12 volts. The problem you have to be careful of is if you're using, and again, I'll go back to the previous webinar we had on that. If you're using a 24-volt system, you have to be careful with single 60-cell modules and enough voltage to charge a 24-volt system. So you have to put two of those in parallel. But again, if you're going to use 60s, just cross the wattage. So whatever wattage you come up with, sizing with a PWM, just use the equivalent wattage of 60-cell modules, or even 72-cell, whatever you want to use there, and just use an MPPT to step it down to your actual system voltage. In a lot of cases, it will be more cost effective, and you might even make your system more reliable. So a lot of good reasons to do that. Okay, loss of load calculations. I'm not going to get into those. Those are ridiculously complicated. There's a whole lot of probability curves and statistical analysis and yada, yada, yada. What I would suggest instead is to go get a commercially available program for that. There are several out that you can purchase. You can just Google for them. There's also, I think there might be some free ones too. I think Enroll has some stuff you can use. I think Canada, I think, also has one as well. We at SunWize use commercially available ones that are specifically tailored to the off-grid solar market, and they're quite reliable and very accurate. So if you're doing this a lot, or if you find the calculations to be kind of a pain in the neck, you may want to consider that. They're actually not all that expensive. They're pretty reasonable actually for what they do. So if it's something that you're doing frequently, you may want to consider purchasing a program that allows you to do that. It'll also make those calculations a lot faster when you start switching around modules, trying to figure out which one fits best in your system and which one is most cost effective. Basically, basically what the loss of load probability is, what they do is they'll basically, as I was saying before, about hey, you might have a failure once every 5 years. That's what it'll do. It'll give you that percentage. It'll say this is the percentage, the chance that you're going to have a failure. You can equate that to maybe once a year, once every 5 year, once every 20 year type of thing. So it'll just kind of equate it to that. Is what those things will do. And getting back to the charge controllers, PWM versus MPPT. I just go again. I refer back to our other webinars on that and different types of charge controllers, which get into how you size those. and how you run those calculations and stuff like that. I referenced our tech notes quite a bit. There's the link for those webinars and some of other engineering bulletins. Okay, I think we've gone way over, but if there are any questions, any other questions on any of that stuff, we can maybe just for a few more minutes try to briefly address those.
Yeah, we can give people another couple minutes to put any questions that they may have in chat. If you're unsure or, think that maybe it's a dumb question, then those are oftentimes the best ones. So don't hesitate if anybody has any questions on what we've covered.
Well, what do you, is that anything coming in there, or are we about done, you think?
I got one more comment that said, nope, thanks. Okay, we got one question on how do you calculate AOR. So maybe we can cover that just one more time.
Okay.
It's simply the power produced by the array in amp hours divided by the load consumed in amp hours.
That's correct. Let me go back to that slide real fast. Way up at the definitions. So the definition itself pretty much tells you what it is. Excuse me. So basically, it's just the ratio of the array amp hours to the load amp hours. Is all it is. So we know what the load is in amp hours per day. If you go, let's just go to our calculations real fast. Use this as an example. So let's see, we've got a, let's go with this one. We know we have two strings, okay? So we have two strings of solar modules. So we're going to multiply those two strings by 3 sun hours a day times 7.8 amps. That tells me then that my solar array is going to produce approximately messed the calculation up. It's part 8 divided by so yeah, so we're going to come up with the, again, we're going to come up with we're going to come up with somewhere around, that's that one, we're going to come up with around the a little bit more than 1.2 because we have a little bit more in this case. So we're going to come up with about, what is this, about 1.23, 1.24, I think, in this case, because of the fact that we've got two strings as opposed to the as the 1.7 we said. So if we ran the calculations, we get the 1.7 was the 1.2, but because we've gone ahead and gone, that's now 2. That number is going to go up higher to about 1.23, it looks like, roughly. Okay, so that's all that is. And again, it's just it's there. It's always, it should never be less than 1. By the way, it should always be greater than 1, because if it's less than 1, then that means the array isn't big enough to support the load. The idea is that, again, it's the ratio of the array to the load, and you always want to have that be greater than 1, because you always want the array to be bigger than the load. Okay.
Rob, I don't think I have anything else, so.
Okay.
Well, actually, hold on. One last question we got coming in. If you're going to manually adjust the array tilt angle during the year, do you use latitude plus 15 degrees for the spring-fall position?
Interesting question. Generally, I would use the latitude plus 15, because that's where you're going to leave it for winter anyway, and winter's always going to be worst case. generally. Most of the time you don't end up adjusting the tilt for seasonally because generally the load, again, most of the time you're going to find your load is going to be constant anyway. If you do have a load that is variable and for some reason it's greater in the summertime, that might be something you want to consider. But for the most part, you're going to find whether it's lading or just anything else, 95% of the time you're going to find that the worst case is going to be the winter. So you're just going to go ahead and set the tilt angle for the winter months, which is about latitude plus 15, and just leave it there the rest of the year and not worry about it. The other problem with that is you'll find that sometimes people forget to do it. Perhaps they set it for summer and then all of a sudden they get an early winter and somebody can't get out to the array to readjust it, and that could be a problem. So usually we just tell people just to kind of set it and forget it type of thing when it comes to that. Okay, well, thank you everybody for your time today. I hope it was helpful and informative. Again, this will be up on our website briefly if you would like to review it at your leisure. And again, I cannot stress enough, if you want more information on this, that IEEE document 1562 is also a very good document. It has a whole lot more information in it with regards to some of the background with this, with the sizing calculations, and it has a nice little worksheet you can use and things like that. So go ahead and review it again and go through some of your calculations. And we look forward to seeing you all at our next webinar next month. Okay, thank you.
Thanks, everybody.